So hello everyone. I know that I am the last thing standing between you and food, so I will try to fit the time. And during the next 45 minutes, I will do a talk about something that can be seen as a follow-up to what Niklas shown us yesterday. And I will show you how to build tools like this. And this tool is actually a TraceCompass filled with information describing what FreeRTOS is doing, what is going on inside the RTOS. So let's divide this huge task into several steps that are easier to manage. First, we need to get some information from FreeRTOS. We need to instrument in some way to get the important things out. Then we need to get our data out of microcontroller and send it to PC in some way. Of course, the PC need to receive that data, probably do some decoding to recover the operations that happened. And finally, we need to build something that our eyes can easier analyze. So we need to visualize these actions in some form. So let's start with instrumenting FreeRTOS. What are the things that we like to see? Most obvious thing is the state changes in task states. So task started sleeping or was blocked on something or just preempted by another task. FreeRTOS uses queues for a lot of synchronization primitives like queues, semaphore, mutexes, and many other things. So we would like to see what is going on with these primitives. Similarly for task notifications, maybe streams, and not strictly RTOS related, but also very useful, the exceptions and interrupts that are handled by our CPU, because they quite often influence greatly what our application is doing. In case of FreeRTOS, we can use a feature called trace hooks, which are just series of macros that are empty by default, but they are called in or used in different places inside FreeRTOS, inside these functions, and we can implement these functions as we as FreeRTOS users, and get access to the FreeRTOS internals, like parameters in function that was invoked, like others of the queue or others of the element being pushed to the queue. And we can also get the information that are not usually visible to the FreeRTOS user, like internals of TCB structure. And we can use this information in trace hooks. So we will implement these hooks to collect the most important information, like address of task that was switched out, or queue that we tried to push to, or mutex that we unlocked, stuff like that. We'll collect the information if the operation was successful or not, or it blocked. FreeRTOS has different API to call from interrupts, so we need to. We would like to see in each our trace event if this function that was called was ISR version or not. As these macros should be put into FreeRTOS config file, we don't want to make it too big, especially putting too much code in macros is not a good way to work with it. We'll limit these macros to only collect the important information, call some external function that will handle all the formatting and serialization of data. And this is a simple snippet of implementation of trace hooks. We start few externs with like nicely named trace events that we are handling. Then we are implementing some macros like task create, which just calls another function. So simple enough. And we can get access to the TCB structure, which is normally hidden from the user. Similarly for the post move to task ready state trace hook, things get a bit more complicated in queue-create trace hook because it's a single hook that is called for each queue-based primitive. So to differentiate between different types of primitives, we need to put some ifs here, which is not great, but still manageable. Important thing is to keep in mind that not everything in FreeRTOS is internally synchronized. So if we would like to, so for example, the creation of queue can be preempted by another creation of queue. So we need to synchronize somehow these two operations, so our output will not be garbaged. We can do it in formatting function, but then this formatting function can be called from ISR. So we need to think where to put the synchronization. The simplest solution is to put the critical section inside this tracecook function. It will slow down the operation a bit. It may move timing inside FreeRTOS a bit, but this is the case with all kinds of instrumentation. So it's important to be aware of this issue and solve it as necessary. Even more complicated example is tracing why task was blocked, which is kind of important information to us. And FreeRTOS gives us this information in a series of trace blocked on something macros. And this is the macros that we are just saving in some global state reason of task switch that will happen in like few instructions later. But we are not sending any trace event right here, so just saving information for a bit later. And again, just series of ifs to handle different cases, because everything is a queue in FreeRTOS. So right now, if we will try to compile our program, we will get a series of undefined reference errors, because we need to implement our trace output functions. And this is binary data, of course. We can reach probably high bit rates, so we need interface that is capable of sending this data out and keep up with incoming data stream. And we also need timestamps, because we need to know when something happened. Just pure list of events is not enough. And we got a nice introduction to ARM trace facilities yesterday. So we can use the instrumentation trace macro cell, ITM, to output data through one of 32 stimulus ports, where we can put as a one unit of data, 1, 2, or 4 bytes. Nice thing is that all these ports share the same FIFO, so the order of writes is preserved, and we can take advantage of this characteristic. And we can enable automatic timestamping, which will send the timestamp packet after data packet that we sent. So we'll get like data, timestamp, yes, stuff like that. But ITM does not define the exact physical interface. The physical interface is the case for trace port interface unit, which again, as Niklas told us yesterday, can be serial wire output, so single pin, or parallel trace port. And this is the combination that I used to output data. And starting from the top, I think it's the most interesting one if you would like to start something to do along the tracing, because you don't need a special trace probe. You can use like cheap FTDI USB UART adapter and get some data. You have some limitation because it will not keep up with like dozens of megabits per second. But if you would like to trace it with some simple application that it's like 1 or 2 megabits per second, you can go with cheap USB UART adapter, and you don't need like buy a JTrace or OpTrace or anything like that. Of course, you can use dedicated trace probe with higher bit rates, or support for like Manchester or parallel trace port to get higher bit rates, and that's probably something they would like to use for more complex application that outputs tons of data per second. Given the ITM capabilities, we can define wire format for our trace events. So how we will serialize these and trace events captured from trace hooks from FreeRTOS. We take advantage of this shared FIFO for all ports, and we can use, for example, port 3 to send control messages indicating event ID and start and stop of event ID, and port 2 to send data. So we can send more than like 4 bytes of data per trace event because, for example, for queue, you would like to send the address of the queue, which is already 4 bytes. Then add some additional flags like was it ISR, was it success operation, what is the updated number of items in the queue. And by defining this explicit packet format, we can easily recover entire packets of data, even if it was truncated in the middle, because we have explicit start and stop. It's very easy to send. We are not using any kind of like stuffing encoding to make to recover packets on the other side. Just outputting, just writes to the ITM registers. It's easy to decode and detect any problems. The overhead is actually only these 2 16-bit packets of data with start and stop. Probably can be made like 8 bits. Just make the event ID a bit shorter. And if we enable relative timestamp in ITM, then timestamp will be sent automatically, and we don't need to include them by ourselves. So pretty straightforward format that can be expanded to like hundreds of events if necessary. And implementation, I used libtrace library from OrbTrace, which wraps the ITM macros and register writes into a bit nicer C functions. And here we see implementation for task created event and task switched out. And the format is pretty explicitly visible here. So we start with header with event ID, then address of the task, then we set the name of the task and footer for that package. And for that packet, for the task switched out, we are using the information that I showed you before in that trace blocked on something trace hook. We are using this information here. So we switched out trace event will include the information about why task was switched out. And yes, I know that I should probably should use RAI for defining the header and footer. Okay, so right now our MCU is toggling some pins very fast and trying to output the data, but nobody is listening. So we need to receive the data on the PC side. And here's the moment when Orbuculum project comes into place. It's an open source project that offers some tooling for Cortex-M tracing features. It's based on the client-server architecture with the Orbuculum process that is responsible for talking to the hardware probe and receiving the trace data. And it outputs that data to series of clients connected via TCP sockets. So you can plug anything to that process. The simplest tool is OrbCat, which just outputs data. It can be used to make very simple logging mechanism. Just write 8-bit characters to some port, and you can just output it as a text with OrbCat, or anything more. OrbTop is a more complex one, as it shows you which function or which line of code is taking the most of the CPU time. It is using the PC sampling from data watch point trace unit, something like that, DWT, and works exactly like Top or Task Manager. OrbDump allows us to dump RAW trace data to file that we can process later using some scripts or another program. And for that processing, we can use native C library for processing that handles all the decoding of trace data and gives us just structures with data, so stream of structures from stream of bytes. Orbuculum supports several hard trace probes. There's of course support for OrbTrace Mini, which Niklas showed us yesterday. It's the trace probe from OrbCode, and it's fast. It's also the debug probe, and it's really fast. Orbuculum can also plug in into JLink server or plug in into any serial port, so you can use USB UART adapter to receive data from serial wire output and get anything through that way. So if your bitrate for trace is low, you don't need anything special to receive that data. And yeah, it loaded. So this is the setup I was working with. On the left, there is a OrbTrace Mini and the EFIM32 development board. The parallel trace port is soldered on the bottom of the board, so you can see it. But it is running a very simple program that just pushes data around in few queues. It's not very production-like, but it allows us to see how the process of building the trace tools works. On the right, on the top, you can see the Orbuculum running, and you can see that it is receiving about a bit over 100 kilobits of data per second, which is not a lot. We could probably just go through the UART here and be okay. And on the bottom, there is an OrbCAD running configured to output data from port 3 and 2, which matches our wire format and control a data port, and rough bytes are spun out on the terminal. And if you remember the wire format, you can see that we have some, on control channel, we have some start and stop packets with data in the middle. So with this, we can probably just grab a paper and pencil and decode what is going on FreeRTOS, but that's not the best way, but it's something. So we need to process the data. We'll start by capturing the data with OrbDump and do all the analysis of the trace offline, so we can easily retune our analysis and try different parameters or do some modifications on the incoming data, like fix, like backfill the task names. So we can. So after running, you see, aha. So this address is the task this. So I can just fill it into output and see what is going on easier without running entire capture process again. And by wrapping libOrb in C types and a bit of Python, we can build our own OrbCAD in 20 lines of code. And on the output is exactly the same output as given by OrbCAD, but this time we are getting to it from Python. And we can see that there is PyOrb SWMSG type that captures the ITM packet, and we can differentiate different stimulus port by checking the specific attribute and output the data as we want. So we are good to go. We can do something with the data. We can decode it into something more useful. For example, some Python structure, a bit of metaprogramming to simplify the coding of all this data. So we have classes for 2 trace events, so task created and queue pushed. Each field corresponds to something in the trace event, to one of the trace ITM writes. And in case of task created, we are using we are treating the first packet in the trace event as int, which is a task reference. Task reference or queue reference later can be resolved to some symbol names, so we can track. So we're building a bit more object-oriented model of our trace data, and so it will be easier to manipulate it later. For queue pushed event, we also have queue reference, which is also an address, but we are splitting the second packet in the trace event into 2 fields, like updated count, so we know how many items are in the queue, and we are decoding some flags. So basically, this is the model that you can build dozens of events as necessary, and then we just map it to different IDs. So we can extend this quite easily. Before we can decode actual packets, we need to recover the timestamps from incoming data. As I said, the timestamps are relative and they're coming after the data packets. So we need to capture everything up to timestamp packet, then yield this entire group as this was received and that timestamp. If our connection to the target is good, then it should be one data packet, one timestamp packet. I never encountered a problem when I got like more than one data packet per timestamp, but that's because I was using the parallel trace probe. So that was not an issue for me. If we lose some timestamps, then we need to recover something or just treat it like a bit later event or previous event. We already got a bit of garbage data at that moment. With timestamp in place, we can do the actual decoding. So we go through each timestamp group, go through each hopefully single message in each group, and if we check if it's the software message, then we proceed with think of wire format. But hello, okay. If we are receiving the exception message, that is the automated message the MCU sends to us. We don't need to decode it anyway in any form because it's already ready to be processed, and we can just output the trace event like exception entered and number of exception. And if it's the trace event that we implemented, we need to build a simple state machine to recover all the data. Here the simple form of the wire format makes it very easy, because we just detect if it's the start pocket or stop pocket packet, and collect data in the middle. We can discover and discard some garbage data, like we lost the start packet for stop packet, or there are like start after start, or some event ID mismatch. So we can filter the not useful data quite quickly. Then you look up the proper type by the event ID, get the constructor, run some Python metaprogramming magic to recover the packet, and yield it with timestamp as necessary. And with a bit of colors, we went from the rough byte stream into something that it almost readable. I mean, you can scan it and see what is going on. And what we can see here is that on the start we see that FreeRTOS is using exception number 14 to switch out and switch in task, because everything is there. We can see the something was pushed to the queue, and there are now 8 items in queue. So with this, we can probably trace see which queue was filled for how to the full for how many seconds. We can of course dump it to file to run some other tools on it. Just simple format with timestamp in seconds, event type, and one field per line. So it's easier to consume by other tools. So we went from rough ITM data stream from bytes. We converted it into Python objects with nice fields which can understand. And this is the point when we could build some scripts or tools that do some automated analysis, get some metrics from the data, like how much time passes between switched out and switched in, what is the runtime for each task. We can build anything, run it automatically. And if necessary, we can just read that trace event and analyze what is going on in our application step by step. And that may be not easier, but it will be it could be useful to do in case of some really hard debugging. So we've built a tool that we have some rough data, but we would like to see what is going on. We would like to see some visualization in it. There are different tools for looking at trace data. We saw Perfetto yesterday. I tried to do something with TraceCompass, which is a tool made by Eclipse Foundation. And it's of course based on Eclipse IDE that can be tuned to do anything. TraceCompass does not have any like native trace format. It is built to consume many different traces, starting from packet capture, some LTTNG, open tracing from like web applications, and I think it will also handle the Perfetto input format, but I'm not sure. But we can also build our own traces based on XML files or plain text files, which allows us to load this trace file into TraceCompass and list the events. If you'd like to build more extended analysis for traces, we need to look into the state system mechanism in TraceCompass, which I'll show you in a few slides. But let's start with defining the trace type. It's not a surprise, it will be XML based. But basically this is like two regexes. First one parses the header of each trace event. Then we get regex that matches each field in that format. If you'd like to do this, there is a nice editor in TraceCompass to define that format. So you can just paste a sample of your trace data and tune the regexes as needed, like a few minutes of work if you remember how to write regexes. Oh, come on. Oh, okay. So with trace type defined, we can load the text file I showed you a few slides before, and we get everything in TraceCompass. We see timestamps, we see event type, and we can see all the extra fields. We can filter it, search through it. We get some basic analysis like at which point in time there were how many events, so like event density charts, and we can just browse through it. There were a few times when I loaded log files from some external tools into TraceCompass to just easier to, because it was easier to browse through it and search. But looking at event list alone is not the most useful thing to do. I would like to get some more structured information from it. And TraceCompass uses a mechanism called state system to describe what is going on inside the system at each given point in time. It is built around a tree-like structure that you can see here, with each node in the tree being assigned a value at some point in time. And these colorful blocks are marking the places where this node in tree is staying at the same value. So for example, we have some task here, and we have state, some task and state, and we can see that it's switching between different states one after another. And this corresponds to the actual events in our trace. This state system provider that converts the events into state system can be implemented in XML. It's doable if you have like low tens of events with pretty simple translation, but it's get pretty tedious and hard to do and maintain if you go into like 30 or 40 trace events. So I would recommend going into Java, sorry. I know you didn't expect Java in embedded conference. But it's not the most complicated part, is just finding out how to create TraceCompass plugin, which is not that well documented. But the actual implementation is just, hey, there is a function and do something for this event, and go one by one. And we are matching the event by name and extracting fields from that event, looking up node in the tree and setting value for that node at specific point in time. The timestamp is got from event. For people who don't want to write ifs or things that ifs shouldn't be used, we can use also some reflection and metaprogramming in Java to simplify it a bit. So we now have a function annotated with type of the event, parameters annotated with with name of the fields, bit of reflection magic to call this function from the state system provider. But now these functions are pretty short and easy to grasp in like one blink of the eye. And I encapsulated the access to the state system in some better named functions, so it's even easier to follow and probably reuse between different events as necessary. It's more tedious to write than hard, because that's like lots of events that you want to load into the state system. It's important to note that you don't need to push everything. You want to fill your state system with things that you will later define some views or things that you want to see. So if the, let's say, a number of updated items in queue is not it's not interesting to you, just leave it in the event. No need to push it into state system. And the entire state system built from my demo application is here. A lot of tasks changes. We can see, for example, how many times task was preempted. There is a task that was blocking on something. You can see what was the blocking object and what operation. And I don't know if you see from the back, but there is a line here, the vertical line, and it's matched. This vertical line is shown on most views in the TraceCompass, and it is synchronized to point to the same timestamp. So you can look for some issue in one view, then switch to another to see what was going on from the different perspective. And it's also synchronized to that selector in the event list, so you can see, this state is not valid. What caused that? Yeah, the event is selected. So we exactly can pinpoint the issue. Of course, state view can be a bit of overloaded view because you see everything. You can define the views, which are subsets of state system. Again, in XML. But here we are defining a tree with which will have node for everything under task in our state system. So one node per each task. It will display the value of the state node under the task and use the name of the node itself for the label. And as states are saved as numeric values, we can define human-friendly names for these numbers. And here we got a bit nicer view with the summary of task states over time, matched to the events. As you see, there is switch to the ready state for some task, and exactly the task ready event is selected. View state system like the tree views is not the only option. You can also define charts. So we can plot the number of items in each queue in very similar syntax. So node for everything under queue. I will display the count as the value of the series and use the name of the node for the series itself. And we got nice chart showing how the queue is filling up. And you can see that selected line is on this flat section of the chart, but there's a queue popped and queue pushed event before it and after it, so it nicely correlates to the chart. It gets a bit fuzzy when zoom out, and some small peaks in the chart would probably not be visible, but it's a matter of like you can draw so small, so short values when zoom out. There's a lot of more features in TraceCompass that I will not cover today because it's not a TraceCompass conference. But powerful feature is called patterns or segments, where you can define state machine that looks for the series of events in your trace, like time between task being switched out and switched in, or how long the mutex was locked, or for how long queue was at its peak capacity. And you can define such patterns and get some analysis for it out of the box. So with selection of each this sequence, there can be many segments overlapping with each other, but that's pretty hard to write on the first time. You can load multiple traces from multiple sources together, synchronize them in time and view as a single trace. So you can, for example, load RTOS trace, then packet capture from Wireshark, and see how packets on Ethernet cable are correlated to the RTOS events. For example, if you got the interrupt when you need it. You can also write scripts for TraceCompass using Python or JavaScript. In scripts, you can build your own analysis, your own state providers, and define views. I tried it, but it was not that great. But I'm hoping that it will improve in future. So you can all build your own trace tools. You need to divide the problem into smaller parts and solve it individually. There are a lot of tools that will help you with it. Orbuculum, which gives you the chip trace probe, and even support for simple UART. Hello? Oh, I'm moving my head too fast. And Orbuculum also gives you tools to work with trace data, not only capture the data. You can use TraceCompass to build whatever visualizations you want and analyze the trace events. And tracing RTOS is not the only thing that we can trace. You can trace file system and how many writes to NAND device are happening and how long they take. If you have some form of embedded scripting language, you can instrument this script engine and output events for function calls and build like profiling for your scripts or better debugging tools for embedded scripts. That's also possible. And while doing it, you will learn tons of internals of how the components in your system work. When I was building the first iteration of these RTOS tracing tools, I learned like tons of what is going on in FreeRTOS for Cortex-M, and by coincidence, like 3 months later, I was deep into debugging the buggy port of some Cortex microcontroller named after Greek god or hero. And this knowledge was very, very useful to me because I was not feeling very, very lost. So thank you for listening to Bits of Java. Few links for Orbuculum, libtrace, and main repository with all the tools that I shown you today. You can mail me, you can Twitter me, or you can find me on Mastodon. Thank you.
Thank you so much for your talk. Are there any questions that we should discuss right now? Yeah, in the back. I'll be right.
I know it.
Hello. So thank you for your talk. Very interesting to see more people interested in trace. I love that. With code instrumentation, you obviously add overhead because, as Nicholas showed yesterday, the ITM FIFO is strangely designed by ARM, and you will have some wait cycles potentially, and you wait for your trace to happen. The Orbuculum stuff also supports J-Link in one way or another. Do you know if they also support RTT as an I/O channel?
I don't think so. I don't remember any mention of RTT.
Okay. Then we maybe should change that, because why I'm saying this is, if you bought the J-Link and you got the tool with J-Link, you will have the RTT as an I/O channel to extract such data, even without using additional pins like SWO or parallel trace pins. We can just use the debug interface that you have designed, so your hardware designers will be happy, and you reduce the overhead that you have with instrumentation that you will always have by like 100 times. This is like...
Yeah, but with RTT we are not using the ARM trace format actually.
No, it's not, but you can print whatever you want.
Yeah, but,
any format.
yeah, but in this case you can just skip the Orbuculum because it's focused on the ARM format.
Okay.
And the coding for that. And if you like to...
So it's more the import to TraceCompass then maybe, or what would be the right interface, you think?
Yeah, so maybe in... in this step.
Yeah, okay, I see.
Yeah.
Okay.
And you can use OpenOCD for that. They have support for RTT.
Yes. Yeah, I know. But it has to be a J-Link with OpenOCD, I heard.
We'll discuss about it.
Yeah, I'm just saying for people that read licenses. Yeah, thank you.
Thanks.
Any other questions? Anybody? I can't see hands, but I'm small, so at my account. Oh, there's one.
So, because we see a lot of C++, have you been using FreeRTOS here with C++, or is it more C code that you're using?
At the company I work for, we are using almost exclusively C++, and for most of our projects we are using FreeRTOS as an embedded RTOS with a bit of our own in-house C++ wrappers around it.
So you use your own wrappers for this, not like POSIX threads or something like that?
No. It's we are not trying to make FreeRTOS look like POSIX or any big operating system, because that can be it will have some quirks at the edge, because they are not the same. But yeah, we have wrappers around FreeRTOS in C++ and write most of our code in C++.
Okay. Thanks.
Any other questions? If not, that probably doesn't mean that there can't be any questions later
I'm not
on.
running away from here, and
Awesome.
I hope to drink some beers today.
So thank you again very much, and let's give him all a round of applause, well deserved.